This is lecture 3, called the ChurchTuringThesis. Church and Turing were two mathematical logicians. It's part of a computer theory course. The title of the course is Introduction to the Theory of Computation. It's a mixed senior first year masters M1 level course. The single author is Sipser, Michael Sipser. Only learned yesterday he's an MIT professor. Here's the textbook, Chinese version. If you buy the English version directly, it'll probably look like this. Second edition. I've got the Chinese version. This text is pretty well the standard text on theory of computation. It's become more or less the Bible. It has its faults, if you've been following me regularly, you'll know. He tends to jump, making assertions that are maybe to him blindly obvious, but not quite so to a lot of other people, the majority of other people. Okay, so this is the text. So we've already done 3 chapters. The chapter 0 was just introductory tool making, describing the tools, conceptual tools, mathematical tools, concepts like sets and so on, needed for this course. Chapter 1 was on regular languages, a certain kind of set of strings. The second chapter was on context-free language, a different kind of set of strings. And this third one is basically it introduces the Turing machine, which is a new type of computational model that's much more powerful than the previous two. In fact, there's an intimate link between category of language, type of language, and the machine that describes it. In the case of regular languages, by definition, they were defined as languages, in other words, sets of strings that were, recognized by finite automata. That was our first type of computer model, the finite automaton, with its states and its switching between states depending on what symbol it's reading at the moment in its input stream. Now, when we get onto the Turing machine, you'll see that it's very similar in many ways, very similar to the finite automaton. I'm getting ahead of myself a little bit, but you'll see this. The second model of a machine that we described in chapter 2 was the automaton that had a stack with infinite memory. The depth of the stack could be infinite, so it could store an infinite amount of information. So it was not a finite machine as was the first model. So obviously it could do far more, but by using the stack. But it in turn had its limitations, because the stack model is essentially LIFO, last in, first out, or FILO, the equivalent, first in, last out. And not everything suits that particular model. And we showed the last board or two, we did detailed proofs that there were certain languages, sets of strings, that were not context-free languages. Now, since the regular language are a subset of the context-free languages, that means that there are languages still sets of strings that the context-free language type machine that describes it, which are called PDAs, push down automata. So in other words, there are tasks, there are languages that the PDA cannot describe. So that motivates us, as I'm saying a bit before in earlier boards, that motivates us to find a more powerful model of a computer, a computing device, a machine, a calculating machine, a computing machine. And this one that we'll introduce in this chapter and on this board. We'll start getting into reasonable details about it. The so-called Turing machine, based on the name Turing, famous name in 20th century mathematical logic, and out of that, as almost like a spin-off, as a side effect, grew the notion from Turing's work of a programmable, general-purpose computing machine, because that's what the Turing machine was. It was general-purpose. Now, we'll need to get into the next chapter 4, before we start describing the universal Turing machine. And strictly speaking, it was the universal Turing machine, the UTM, that was so inspirational to a lot of people who felt that, hey, now we have the technology, because they had electronic valves and that sort of thing at the time. It was in the 1940s, that people seriously started thinking, well, we could actually implement a universal Turing machine. We could create a machine that would be programmable and general purpose, and could compute things for us, mathematics, and make decisions, and bookkeeping, and all sorts of business uses. Well, extremely useful. There might even be a market across the whole of the United States for 5 of these machines. Some IBM director actually said that. So embarrassing. Good. All right. So we need a new model for a machine, more powerful than the finite automaton or the PDA, the push-down automaton. The automaton with a stack. Those two models not powerful enough. So we'll introduce a new kind of machine. So the finite automaton and the PDA are too restrictive in their capacities. They're very weak capacities relative to the Turing machine. So let's now talk about this model invented by Turing. So this will be section 3.1. So chapter 3, and the first section in this chapter. Let's see how many sections there are in this chapter. It's a fairly short chapter as this text goes. It's only about a bit over 20 pages, so it won't take too long. 3 sections. Section 1, Turing machines. Section 2 is variants, variations of Turing machines. In section 3, the definition of algorithm. What actually is an algorithm, and it'll be defined in terms of the Turing machine. Right? Now, before I get into the details of the actual machine, Turing himself is a fascinating character, one of the major thinkers of the 20th century, and due to his vision, we now live in an era of the computer. So you could quite easily argue that he is the father of computation. Although I think poor old Babbage, who was a century ahead of him, if only Babbage had been a little more practical. I mean, he kept reinventing better ways of computing and never actually finished, in the sense of engineered his designs. So the British government, who was funding him, eventually lost patience and stopped the funding. So the world was denied the creation of computers by Babbage by a century. One of those fascinating what-if scenarios in history. If Babbage had just been a little bit more practical, a bit more pragmatic, and actually finished an earlier design before totally abandoning it and spending full time on his next design. Okay, so Turing, he was a mathematician, essentially. He went to King's College in Cambridge University in England in the 30s. And this model that we're going to describe, which he invented, published in 1936, he was all of 23, 24 years old. Amazing, isn't it? So I think Heisenberg, with his uncertainty principle, and the father of the modern quantum mechanics, was a similar age. So if you're a genius, you tend to manifest